Here we are continuing our previous lecture, that means the lecture number 13, with a problem. Here in this very problem you are given to extend this set of vectors to an orthogonal basis of the Euclidean space R3, which is basically a Euclidean space with the standard inner product. You all know what basically the standard inner product is. Standard inner product is the component wise multiplication and the addition of the corresponding term. Okay. So you have to extend this set of vectors to a orthogonal basis. To check this, to construct this, we are considering this first vector 2, 3, -1 of this collection as the alpha 1 vector. Alpha 1 vector equal to 2, 3, -1, and the second vector of this collection 1, -2, 4 as the vector alpha 2. So alpha 2 equal to 1, -2 and -4. Let us now check whether alpha 1 and alpha 2 are two orthogonal vectors or not. Here we have calculated the inner product value of alpha 1, alpha 2. The first component of alpha 1 is 2. The first component of the alpha 2 vector is 1. So the first component of this inner product alpha 1, alpha 2 will be 2 into 1. The second component of the alpha 1 vector is 3. The second component of the alpha 2 vector is -2. So the second component of this inner product alpha 1, alpha 2 will be 3 into -2. The third component of this alpha 1 vector is -1, and the third component of the vector alpha 2 is -4. So the third component of this inner product is -1 into -4. After calculation we have this equal to 0. So alpha 1, alpha 2, this is equal to 0. Consequently alpha 1 and alpha 2, these are two orthogonal vectors. The vector space R3 is of dimension 3, and we all know the standard basis of this vector space R3 is this set of vectors 1, 0, 0, 0, 1, 0 and 0, 0, 1. This set of vectors is the standard basis for the vector space R3. We are considering any one of these. Suppose here we have considered this vector 0, 0, 1 and renamed it as alpha 3 equal to 0, 0, 1. We are considering in such a way that the considered vector here, as we have considered alpha 3 equal to 0, 0, 1, and these two vectors alpha 1 and alpha 2 be linearly independent. To check the linear independence, we have considered this determinant. We are already familiar with this type, how to check the linear dependence or independence in the vector space 2, in the vector space 1. Here this first row members 2, 3, -1 are the components of this first vector alpha 1, 2, 3, -1. Similarly 1, -2, -4, this is the second row, each and every member being the components of this alpha 2 vector. Similarly the third row of this determinant is 0, 0, 1, each and every member being the component of the alpha 3 vector 0, 0, 1. And if we calculate this determinant, that means if we expand, here I have expanded with respect to the third row and the calculated value is -7. That is actually not equal to 0. And this being not equal to 0, the determinate value, we can say the vectors alpha 1 and alpha 1, alpha 2 and alpha 3 are linearly independent. This is alpha 1, alpha 2 and alpha 3 is linearly independent. And this alpha 3 vector which we have considered from the standard basis is not in the linear span of these two vectors alpha 1 and alpha 2 which are given. And also alpha 3 is a vector from the vector space R3 or specifically from the Euclidean space R3. So we shall construct from here such type of a vector beta by this. Beta equal to alpha 3 minus C1 alpha 1 minus C2 alpha 2. Beta equal to alpha 3 minus C1 alpha 1 minus C2 alpha 2. Where C1 is the scalar component of the vector alpha 3 along the vector alpha 1, C2 is the scalar component of the vector alpha 3 along the vector alpha 2. We are constructing this vector beta because from the previous class we know that this beta vector would be orthogonal to each and every member alpha 1 and alpha 2. Alpha 1 and alpha 2 of the given set of vectors. Try to recapitulate, try to remember what was basically the theorem that we have already learned in our previous class, that beta equal to such form, this is orthogonal to each alpha I vector. And using this theorem we are constructing this vector beta. And we also know how to calculate the scalar components C1 and C2. We are using that rule. C1 being the scalar component of the vector alpha 3 along the vector alpha 1, we have written here C1 equal to the inner product of alpha 3 alpha 1 divided by the inner product of alpha 1 alpha 1. And we also know how to calculate this inner product. This alpha 3 vector is equal to alpha 3 vector is equal to 0 0 1. The first component of this alpha 3 vector is 0 and the first component of this alpha 1 vector is 2. So here we have written this first element as 0 into 2. The second component of this alpha 3 vector is 0 and the second component of this alpha 1 vector is 3. So we have written the second member as 0 into 3. The third member of the alpha 3 vector is 1. Third component of the alpha 3 vector is 1. Sorry, not member, this is actually the component. Third component of the alpha 3 vector is 1 and the third component of the alpha 1 vector is minus 1. So the third member we have written 1 into minus 1. And this is the inner product of alpha 1 in alpha 1. Alpha 1 equal to the vector 2 3 minus 1. So the inner product of alpha 1 would be 2 square 2 into 2 2 square plus 3 into 3 3 square plus minus 1 into minus 1, that means minus 1 whole square. So we have written in this denominator portion 2 into 2 plus 3 into 3 plus minus 1 into minus 1. After calculation we have this value minus 14, C1 equal to. And also C2 being the scalar component of this alpha 3 vector along the vector alpha 2, we have calculated C2 scalar component. This is equal to the inner product of alpha 3 alpha 2 vector and the inner product of alpha 2 alpha 2. Similarly, as we have done in our foregoing case C1. So their calculated value is minus 4 by 21. And beta equal to alpha 3 minus C1 alpha 1 minus C2 alpha 2. In places of C1 and C2, we have substituted the corresponding values. And the calculated value of this beta after simplification of these two lines, we have this 1 by 3 minus 1 by 6 minus 1 by 6. So the orthogonal basis would be the first two vectors alpha 1 and alpha 2 which are given, and the third vector beta which we have calculated. Here we have written this, and this collection of vectors will be the extended orthogonal basis of R3, Euclidean space R3. And if you are given to write down the corresponding orthonormal basis, merely you have to divide each and every vector by its norm. So in this case, the orthonormal basis of these orthogonal basis would be this set of vectors. Here we have calculated the norm of each and every vector forming this orthogonal set of vectors. The norm of the vector 2, 3, minus 1, this vector is equal to root 2 square, 3 square, minus 1 square, and after calculation we have this is equal to root 14. So we have divided this first vector by root 14. Similarly, we have calculated the norm of this vector 1, minus 2, and minus 4. This is equal to root 1 square, minus 2 square, minus 4 square. After calculation we have this equal to root 21. So we have divided this second vector by root 21. Similarly, the norm of this third vector is 1 by 3 square, minus 1 by 6 square, minus 1 by plus 1 by 6 whole square root. After calculation we have this is equal to 1 by root 6, and if we divide the vector alpha 3, this vector, by this norm 1 by root 6, this will be after calculation this 1 by root 6 into 2 minus 1. So we have written here that very value 1 by root 6 root 2 minus 1. This is the corresponding orthonormal basis, and the orthogonal basis is this set of vectors. Okay.